Hello, my name is Kirk Saunders, and for my final project for Numerical Methods, I solved the inverse kinematics problem for a planar robotic arm. So a little bit about the problem to start with. Consider a planar robotic arm like the one pictured here. It consists of a series of solid links connected end on end by pivot joints. And you can imagine that if you change the angles at each of these joints, the positioning of the robot will change. In particular, we are interested in the end of the robotic arm, in this case, that is P sub 4. This is called the end effector of the robot. The inverse kinematics problem consists of finding joint angles such that the end effector is positioned at a desired location. In our diagram, this would mean that we want to find angles a sub 1, a sub 2, and a sub 3, such that P sub 4 is equal to P sub f, where P sub f is the desired end effector position. So now onto the solution method I used for this problem. First, if we write the equation of the end effector's position as a function of joint angles, and we set it equal to P sub f, we find that we have a nonlinear system of equations to solve. So given a robot with n links, we have n unknowns, because there's one unknown for each joint angle, and two equations, because there's one equation for each positional component, and since we are in 2D space, there are two positional components. So as we learned in this course, we can apply a vectorized form of Newton's method to solve nonlinear systems of equations by using the Jacobian matrix of the system's vector function during the Newton's method update step. However, we only ever solved systems of equations with equal number of unknowns and equations. This is because whenever we have equal number of unknowns and equations, the vector function in matrix form is square and thus invertible, so we can solve for the increment during the update step quite easily. However, in the case that we have n greater than or equal to 3 links in our robot, the Jacobian matrix is non-square, so we must use what's called the Moore-Penrose pseudo-inverse for the method to converge properly. A little bit more about the Moore-Penrose pseudo-inverse and why it's needed. So since our system can have more unknowns than equations, it actually has infinitely many solutions in many cases. We run into some issues when trying to use MATLAB's backslash operator during the Newton's method update step, but this is solved by using the Moore-Penrose pseudo-inverse to solve for the angle increment during the update step instead. So without getting into too much detail about what the pseudo-inverse is, just know that for any matrix there exists a pseudo-inverse of that matrix that is unique, and it has many of the same properties as the regular inverse, but not quite all of them, but it also has some more properties that are also useful. And whenever we use this pseudo-inverse to solve for the angle increment during the update step, it does allow Newton's method to converge, whereas it did not with just MATLAB's default backslash operator for solving the linear system during the update step. So now I'm going to show an interactive demo of my results and show that the solver is indeed solving inverse kinematics problem. What you'll see is a robot positioned in a 2D plane, where the base of the robot is positioned at the origin, and we've plotted a function in the plane, and we're going to have the robot actually trace this function over time. So you should see now an interactive demo. The robotic arm is tracing a circle in the plane. And you can see over time, it does keep tracing it. And what's happening is at each update step, we're calculating the next position along the parametric function, which is in this case a circle. And we're having the solver actually solve inverse kinematics such that the robotic arm puts its end effector at that location. So now we'll take a look at another function. So now here's a slightly more complex function. We've also changed the configuration of the robotic arm just to show that the solver actually works for any configuration. In this case, I just changed the last link. I made it a little bit longer. You can see it's tracing just fine. And we'll show another one. So here's another function that's being traced. It's a little bit more complex, and it's also moving faster. And you can see that the robotic arm traces it just fine. So this is a nice interactive demo showing that the solution that I wrote does work, and it is fast enough to at least work in real time. If you were to write this in another language other than MATLAB, for example, in a real-time solution in a robotic environment, you would probably write it on some sort of microcontroller. It would be even faster. So this is all I have for this demo. I hope you enjoyed.